Good morning, everyone. In the last lecture, we discussed about eigenvalues and eigenvectors and how to determine eigenvectors and eigenvalues, right? Today, we'll start the topic transfer function, transfer matrix. Transfer matrix. Actually, if we have a number of inputs, then the transfer function will be a matrix containing transfer function of all the input output combinations. But if we have single input single output, then the transfer matrix will be a simply transfer function, right? Since with the help of this state space analysis, we can analyze a multi-input multi-output system. Therefore, we have the topic transfer matrix, right? The matrix relating Laplace transform of output to the Laplace transform of input of state space representation of a control system is known as transfer matrix. The matrix relating Laplace transform of output to the Laplace transform of input of state space representation of a control system is known as transfer matrix, right? We have the state model as x dot is equal to ax plus bu and y is equal to cx plus du, where x is a state vector, u is input, y is output, a is system matrix, b is input matrix, c is output matrix, and d is relation between input and output, right? After taking in Laplace transform of state model, we get s axis minus x naught. I am considering the initial conditions. S axis minus x naught is equal to a axis plus b us and ys is equal to c axis plus d us, right? And if I consider for transfer function x naught is 0, x naught is equal to 0, then our equation state model, Laplace transform of state model becomes s axis is equal to a axis plus b us and ys is equal to c axis plus d us, right? From here, from this equation, we have s minus a axis is equal to b us, or xs is equal to, if A is a matrix, then this will be Si minus A. Si minus A inverse B US, and we know this term is phi S B US. This is xs. Put this value in equation of ys, in output equation, then we get ys is equal to C phi S B US plus D US, right? And I told you, in case of single input single output, this D is 0. But now this time I am taking multiple input multiple output, then ys will become C phi S B plus D US, right? And now what will be ys over us? This is transfer matrix, and this transfer matrix will be equal to C phi S B plus D, right? For single input single output system, what will be the transfer function? Ys over us is equal to simply C phi S B, right? So if I want to calculate transfer function of any state model, we can calculate it from here, C phi S B, right? For example, if I have a system like x dot is equal to 0 1 minus 2 minus 3 xt, or x simply, plus 0 1 u, and y is equal to 1 0 x, right? And I have to find out the transfer function of the system. So first of all, find out what are the matrices. Matrix A is 0 1 minus 2 minus 3, matrix B is 0 1, and matrix C is 1 0. So first of all, for transfer function, what is the transfer function? Ys over us is equal to C phi S B. Here D is 0, so C phi S B. So first of all, we have to find out phi S. What is the phi S? Phi S is Si minus A inverse. Si minus A inverse. And what is Si minus A? Si minus A matrix is S minus 1, 2, S plus 3. And what will be Si minus A? First of all, we have to find out determinant of Si minus A. So determinant of Si minus A will be S into S plus 3, S plus 3 plus 2, or S square plus 3S plus 2. S square plus 3S plus 2, or S plus 1 S plus 2, right? So what will be the inverse? Inverse of this si minus a inverse will be si minus a will be in the place of s we'll write s plus 3. This is the short trick, divided by determinant this s plus 1 and s plus 2. Here, since it is minus 1, this will be plus 1. 1 divided by s plus 1 s plus 2. Here it is 2, so it will be written as minus 2 divided by s plus 1 s plus 2. And here in the place of s plus 3 we will write s plus 1 s plus 2. This is the short trick for 2 cross 2 matrix for determine inverse of the matrix, right? After this, what is our C phi s b? Ys over us is equal to C 1 0 phi s. Let this one is f1, f2, f3, f4. f1, f2, f3, f4. And what is b? 0 and 1, right? Now multiply. First of all, multiply these two matrices or multiply these two matrices. So we multiply these matrices. So here we will find that f1 plus 0. So f1. And here f2 plus 0, f2. And multiplied by 0, 1. Now multiply it as f2. This will result as only f2. And what is f2? We have f2 is 1 over s plus 1 s plus 2, or simply 1 over s square plus 3s plus 2. This is our transfer function, right? This is our transfer function. In case of multiple input multiple output, let here we have 1 1, and here also we have 1 1. Then what will be the solution? What will the transfer function? Then if I multiply these two terms, then we have f1 plus f3 and f2 plus f4. And here we'll find our transfer function as this plus this, है ना? So this will be f1 plus f3 plus f2 plus f4, means f1 plus f2 plus f3 plus f4. This will be our final transfer function of two input to output system. ठीक है, तो फाइनली आउटपुट क्या बन जाता है? f1 प्लस f2 प्लस f3 प्लस f4. और ऊपर क्या क्या है, इन सबको अगर प्लस करें तो s प्लस 3 प्लस 1 माइनस 2 प्लस s डिवाइड बाय s स्क्वायर प्लस 3s प्लस 2, और this will be equal to here we get 1 314 2s plus 4 divided by s square plus 3s plus 2. This is our ys over us. In case we have b is equal to 1 1 and c is equal to 1 1, then, right? So this is the method to find out transfer function. Again, this is not a multiple input multiple output. Sorry, I am mistaken. If we have multiple input multiple output, then this will be like 1 0 and 0 1. This is, and here 0 1 and 1 0, let it like this, and then we will solve this. Then we will solve this as, just a minute, here I am solving this. Then if I multiply these two, what will be the result? First of all, this 1 into f1 plus f3 plus 0. So here will be f1 and here f3. Here f2 and here f4. Then 0 1 1 0. Here what will be the solution? After multiplication, f1 0, f2, here f1, here f4, and here f3. This is our for 2 input 2 output system transfer function. So this will be the function, transfer function of one another input output. This is the transfer function of another input output. This is the transfer function of another input output, like this, right? So this is the solution. This is our transfer function or transfer matrix. After that, the next topic is controllability and observability. We will solve some other examples for regarding this transfer matrix after controllability and observability. So, controllability. Controllability. Let me draw a diagram. This will clear the controllability's concept. Here u, and here we have final output y, right? Initial condition is at t naught. In this picture, in this diagram, what is the state equation? From this diagram, what is the state model or state equation? State equation is x1 dot is equal to 2x1 plus x2 plus u. And what will be the x2 dot? X2 dot will be 2 minus 2 x2, only minus 2 x2, nothing else. And what is y? Here y is just x1, right? So from this relation or from this diagram, we see that we do not have any control of this u on this state x2. We do not have any control of this input u on this state x2. We cannot control this state with this input u. And if any state is like this, that it is independent of input, it is not connected to input, or it is not controlled by the input, then the whole system becomes state uncontrollable. State uncontrollable. Right? So the controllability is in relation to transfer of a system from one state to another by appropriate input controls in a finite time. The controllability is in relation to transfer of a system from one state to another by appropriate input controls in a finite time. What is finite time? Finite time means from this time, from initial time t naught to final time tf. From initial time t naught to final time tf. Means in the interval tf minus t naught, if I control a state, then the system is controllable. If there is a relation in system input and state, then the system is controllable. Otherwise, the system is not controllable. Here, in this diagram, x1 is dependent on input u, but the input has no control over x2. This x1 is dependent upon u, but the x2 has no control, but the u has no control over x2. Thus, it is not possible to operate this state x2 from its initial state t0 to tf. From its initial state t0 to tf, we cannot drive this system with this input. Okay? And thus the system is state uncontrollable. Therefore, a system is said to be controllable if it is possible to have an input u to transfer the system from any given initial state initial state xt naught to any given final state x tf over a specified interval of time tf minus t naught, the system is said to be controllable if it is possible to have an input u to transfer the system from any given initial state xt naught to any given final state xtf over a specified interval of time tf minus t naught. This is the definition of controllability. This is the definition of controllability, right? And for controllability, for testing the controllability, that the weather system is controllable or not, we perform a test. We perform a test by using a matrix called controllability test matrix. Controllability test matrix. And what is the controllability test matrix? It is derived from here. Like we have state model as x dot is equal to ax plus bu, ax plus bu, and y is equal to cx plus du. This is our state model. The condition under which an input control can drive the system from initial state x naught to final state xn, right, concerns controllability. The condition under which an input control can drive the system from initial state x naught to final state xn concern controllability. And in this case, we can write x1 as a x naught plus b u naught. x2 will be a x1 plus b un, or a x naught plus b u naught plus b un, means we put this value from here and then we get a square x naught plus a b u naught plus u1. x3 a x2 plus b u2, and after replacing this value here we get a cube x naught plus a square b u naught plus a u1 here plus b u2 b u1 here. Just a minute. This is bu1. A B u1 plus b u2 and so on. We get xn is equal to a raised to n x naught plus a raised to n minus 1 b u naught plus a raised to n minus 2 b u1 and so on, and finally we get b un minus 1, and this can be written as, if I manipulate this equation, xn minus an x naught is equal to, this can be written as b from here, ab a square b a n minus 1 b multiplied by un minus 1 un minus 2 and so on, here u1 and u0, right? You can write this equation in matrix form like this, and LHS in this equation, LHS means xn minus a raised to n x naught, xn minus a raised to n x naught in this equation gives initial and final state. This is final state and this is initial state. Gives initial and final state. So for the system to be fully controllable, it is necessary and sufficient that the n cross nm matrix U has the rank n. And what is the n cross nm matrix? U, it is B, this matrix, this one, B, A, B, A square B, and up to A raised to n minus 1 into B. Means for the system to be fully controllable, it is necessary and sufficient condition that this matrix has the rank n, right? And if this is the condition is true, then the system is controllable. And this U matrix is called controllability test matrix. Controllability test matrix. right? If this matrix is in condition, if U is a square matrix, then the condition for controllability is determinant of U should not be equal to 0. It means the matrix should not be singular. Should not be singular, right? And if the matrix is not singular, means determinant is not equal to 0, then obviously the rank of U will be n, right? Obviously the rank of U will be n. So both the conditions are true, whether its rank should be equal to n or determinant of U should not be equal to 0. For example, let we have a system like x1 dot is equal to x1 plus x2 plus U, and x2 dot is equal to minus x2, and in that case the matrix will be x1 dot x2 dot, here 1 1 0 minus 1, x1 x2 plus 1 0 U. So matrix A is equal to 1 1 0 minus 1, and matrix B is equal to 1 0, and controllability test matrix then is equal to, since n, A is system matrix which is n cross n matrix, so what is the value of n? N is equal to 2. N is equal to 2, and if n is equal to 2, this U matrix will go up to a raised to n minus 1. A raised to n minus 1 means a raised to 1, because n is equal to 2. So U matrix will be B colon AB, right? So here we write matrix B 1 0, and matrix AB will be, multiply this and this, so 1 into 1 1, 1 into 0 0, 1 plus 0 1, here 0 into 1 0, minus 1 into 0 0, yeah 0, and it is clear that its rank of U is not equal to 2 or n, right? Therefore the system is uncontrollable. The system is uncontrollable, right? And this test is called Kalman's test. This test is called Kalman's test because first Kalman has named this matrix as controllability test matrix, and he only derived the equation. Another question, another example we have. Directly I am writing matrix A, matrix B, and matrix C. Which is matrix A. For controllability, we need only two matrices, A and B. So I am writing just two matrices, minus 0.50, 0 and minus 2. And matrix B is 0, 1. Right? Now, I have to test whether the system is controllable or not. Right? Again, n is equal to 2. So, u will become 0, 1, and multiply these two values. Here 0, here 0, this will be 0. Again here 0, here minus 2, this will be minus 2. Again rank of u is not equal to n or 2. Therefore, system is uncontrollable. Therefore, the system is uncontrollable. Right? Let us take another example. In an example, we have given matrix A is T1 0 0 T 0 0 0 T square, and matrix B is given as 0 1 1. In this case, n is equal to 3, so u will be B, AB, and A square B. So first of all, we'll find matrix AB. AB matrix will be, multiply these matrices, these values, T into 0 0, 1 into 1 1, and again 0. So here will be 1. Here 0 into 0 0, T into 1 T plus 0. So here we'll find T, and here 0 0, so 0 0, and T square into 1 T square. This is matrix AB. And now A square matrix. A square matrix, we will find it as T1 0 0 T 0 0 0 T square. Again write this matrix T1 0 0 T 0 0 0 T square, and multiply these two matrices. We will have T square here, T plus 1, T plus T, 2T, right? And after that we'll have here 0, here 0 0 0, here T square 0, and here 0, again 0 0, and T raised to 4, A square matrix. So what will be A square B matrix? Multiply this matrix T square 2T 0 0 T square 0 0 0 T raised to 4 with 0 1 1, here 0 2T, here 0 T square, and here T power 4. This is our A square B matrix, right? And now U matrix will be 0 1 1 AB matrix 1 T T square and A square B matrix 2T T square T raised to 4, right? And now solve this for since it is square matrix, so we will check it as determinant of U. What is the determinant of U? Here minus t power 4 minus 2t cube plus t square minus 2t square, right? So this becomes minus t power 4 plus 2t cube minus t square, and after taking t square as common we get minus t square as common, we get t square plus 2t minus 2t plus 1, right? And if t is 0, this will depend upon the value of t. If t is 0, then only the matrix is 0. Otherwise, the matrix is like the system is controllable. Otherwise, the system is uncontrollable, right? So, controllability depends upon the t. This is all about controllability. Next video will discuss the topic observability.